You know, when you read a brilliantly written essay, there is this underlying assumption of continuity.
Right, yeah. Like the ideas structurally build on each other.
Exactly. You picture the writer sitting at a desk, right? And they're holding a single evolving train of thought in their head from the very first sentence all the way down to the concluding paragraph.
The context is just held securely in their working memory the entire time they're drafting.
Yeah, but if you apply that same human expectation to how artificial intelligence actually generates text, I mean, the illusion just completely shatters.
Oh, absolutely. It's a totally different reality.
And we are diving into that fragmented reality today. So welcome to a custom-tailored deep dive specifically designed for you. Today we're exploring the absolute cutting edge of generative AI architecture.
We have a really fascinating state-of-the-art paper to dig into.
We do. It's from a team of researchers at Princeton, Ziancai, Xinyuzu, Yihidong, Yingwei, and Sanjeev Arora. And the paper is titled T2MLR, Transformer with Temporal Middle Layer Recurrence.
And, the central premise here tackles a fundamental structural flaw in modern AI because the models we rely on, they're incredibly powerful, but structurally, they suffer from the severe step-by-step amnesia.
Yeah, they're trapped by the very mechanism they use to output language. So our mission for this session is to explore this flaw in how AI models, quote unquote, think over time.
Right.
And we're going to examine how this remarkably clever architectural tweak, essentially giving the AI a continuous short-term memory in its middle layers, drastically improves its reasoning skills.
It's a huge leap forward.
And here's where it gets really interesting. This isn't just a theoretical idea that requires like $1 billion supercomputer to test. They built a practical upgrade that can actually be retrofitted onto existing models without starting from scratch.
Which is huge. Because in a world where we increasingly rely on AI for complex, multi-step problem solving.
Like coding or, deep logical deduction.
Exactly. For those tasks, understanding the mechanics of how these models transition from being mere text predictors to actual reasoners is just crucial. I mean, a text predictor is just calculating the statistical probability of the next word.
Right, it's just guessing.
Yeah, but a reasoner has to hold a complex, abstract concept in its latent space and actually manipulate it over time.
Okay, so before we can fully appreciate the brilliant solution the Princeton team engineered, we really need to understand the frustrating limitation of current AI models.
We have to look at the structural bottleneck.
Right. If you look at standard transformer architectures, the researchers refer to them as being strictly token-centric.
Meaning the entire computational pipeline is optimized for one very narrow outcome, which is producing a single discrete token at the end of the forward pass.
Just one piece of a word.
Yeah. During autoregressive generation, the model does this incredibly rich, high-dimensional computation across dozens of attention heads to figure out the next step in a reasoning process.
It's doing all these serious mental gymnastics, holding thousands of variables.
But then it hits what the paper calls the unembed decode embed bottleneck. To actually output a word, the model is forced to compress all of that rich, nuanced internal thought back down into a single, sparse, one-hot vector.
So it's just a discrete integer representing a token ID?
Exactly. And that discrete representation is the only input it gets for the next step.
It just throws away the multidimensional math. Okay, let's unpack this. It's like having a team of brilliant scientists working out a massively complex physics equation on a giant whiteboard.
I like this analogy, yeah.
Right, so they're doing incredible nuanced work. But to pass their progress to the next shift of scientists, they are mathematically forced to erase the entire whiteboard and write just a single word on a tiny sticky note.
That is exactly what happened.
And then the next shift has to look at that one sticky note, reference the manual, and try to reconstruct the entire mathematical state from scratch.
It's a very accurate way to visualize it. The rich thought is unembedded, decoded, and then re-embedded. And because that static token is the only input, intermediate reasoning states simply cannot persist across time.
The model structurally cannot hold on to its own thoughts.
No, it can't.
Which totally explains why AI sometimes completely loses the plot on long logic problems. It's literally reconstructing its logic from a trail of sticky notes.
Yes.
Now, if current models are throwing away their logic at every word, how did we even get this far? I mean, what were the previous workarounds for this?
Well, the previous attempts to fix this generally fell into two camps. The first is prompting the model to use explicit chain-of-thought reasoning.
Oh, where you force the AI to write out its entire internal process in verbose text.
Right. Basically making the scientist write 1,000 sticky notes instead of one.
But that eats up your token limit, right?
Exactly. It increases latency, and it relies heavily on the assumption that complex reasoning can even be perfectly translated into text, which isn't always true.
Right, sometimes math is just math. What was the other workaround?
The other approach was modifying the architecture to loop over all the transformer layers multiple times for a single token, like in universal transformers.
Oh, I imagine that solves the amnesia, but it has to be computationally brutal.
Oh, it's incredibly slow. If you loop the entire network, say, 3 times per token, you are essentially tripling your inference latency. It's so costly at inference time.
Okay, so we need a way to let the scientists keep their whiteboard across shifts, right? Without externalizing everything to thousands of sticky notes and without grinding the entire system to a halt.
Exactly. And that brings us to the T2MLR solution.
Transformers with temporal middle layer recurrence. So how does this actually work?
Well, instead of forcing the recurrent information, the memory of the last step, to live outside the network in the input embeddings, T2MLR builds an internal bridge.
Inside the layers themselves.
Right. It caches the continuous representation from a deeper layer of the previous token, and it fuses it directly into an earlier layer of the current token.
Using a gated recurrent pathway. But wait, if the problem is losing the state at the output, why target the middle layers specifically? Why not just pass the final state to the very first layer?
Because that assumes every layer in a transformer is doing the same type of work.
Yeah.
Mechanistic interpretability analyses show us that's not true.
There's a division of labor.
A strict division. Early layers just do lexical and syntactic processing. They figure out the grammar.
They're just parsing the language.
Right. And the late layers almost exclusively project the vocabulary. They just pick the right word.
Okay, so the front reads the syntax, the back formats the speech.
Exactly. Which leaves the middle layers as the primary locus of abstract reasoning. By connecting the middle layers over time, T2MLR puts the memory exactly where the thinking actually happens.
Wait, so instead of the AI having to reconstruct its entire reasoning state from scratch using only the previous word, it gets to hand off its raw, complex thoughts directly to the next step's reasoning center.
That is exactly what it does.
So what does this all mean for actual performance? Like, internal neural bridges sound elegant, but how do we know this actually works?
To prove this middle layer handoff works, the researchers designed this brutal synthetic test that traditional models inherently fail. It's called the S5 retrieval task.
S5 retrieval. Break down how that works, because it sounds like a torture test for AI.
It basically is. It perfectly isolates 2 things: in-context retrieval and state tracking.
Okay, retrieval meaning.
Looking back at a dictionary of variables provided in the prompt. Fetching static facts. Standard transformers are great at that.
Right, they just use attention to look back.
But then comes state tracking, keeping track of how those variables change over a sequence of up to 48 states.
Oh, wow. So you have to remember the initial rules and track this complex, evolving game state simultaneously.
Exactly. And standard transformers fail at state tracking. They mathematically need big O of log n layers to track states properly because they don't have an evolving latent state.
They have to recalculate the whole history every single time.
Yes, which overwhelms the attention mechanism. Now, on the flip side, recurrent neural networks, like RNNs or LSTMs, they are great at tracking state over time.
Because they carry a hidden state forward.
Right. But they fail at retrieval because they compress everything into a fixed dimensional state. The early facts get overwritten.
Ah, so transformers have the book open but can't follow the plot, and RNNs follow the plot but throw away the book.
That's a great way to put it. And T2MLR beautifully marries the two. The transformer backbone keeps access to the input sequence for retrieval, while the recurrent pathway handles the evolving latent state.
Best of both worlds.
Exactly. And the results. The baseline 4-layer transformer and the 4-layer LSTM completely flatlined.
Just to be clear for you listening, this isn't just about scoring a few points higher. The traditional models literally collapsed on the exact match metric as the sequences got longer.
Dropped to near 0, while T2MLR attained near-perfect in-distribution exact match accuracy.
It essentially solved it. But, okay, let me offer some pushback here. How does this semantic alphabet test translate to real-world math and logic?
That is the big question. Moving from synthetic tests to actual reasoning tasks reveals a lot, including a highly surprising quirk about how T2MLR operates best.
Okay, let's talk real-world datasets.
When tested on actual reasoning datasets, the results were staggering. On a variable assignment task, Accuracy jumped from 49.4% up to 93.9%.
That is a massive leap.
Right. And Hotpot QA, the easy version, jumped 25%. GSM OG, which is a math task, jumped 18.7%.
Because it's not relying on the sticky notes anymore, it actually feels the mathematical weight of the concepts it derived earlier.
Exactly. But the most fascinating finding from their 10 billion token pre-training run is the recurrence configuration itself.
Well, logically, if connecting layers over time is good, then looping the entire brain, all 30 layers, must be the absolute best, right?
What's fascinating here is that the data completely debunk that.
Wait, really?
Yeah. The data shows that applying recurrence to only a localized middle layer block, as little as 20% of the network, actually outperforms full layer recurrence.
Just 20%.
Specifically layers 13 to 18 out of a 30-layer model. It proves that recurrence is most valuable only where abstract processing is most active.
Because if you loop the early layers, you're carrying forward grammar that isn't relevant anymore.
Right, you're just introducing noise. It proves that deeper or bigger isn't always better if it's in the wrong place.
Precision matters more than scale, which naturally brings us to this so what for the industry. I mean, a model that reasons better is great, but if it takes 10 times the computing power, no one is going to use it.
Exactly. Efficiency is everything in production.
So how does T2MLR perform in the real world?
Well, unlike those loop transformers that multiply the compute by the number of loops, T2MLR adds at most an 8% per token inference overhead.
Just 8%. That's barely a blip compared to generating paragraphs of chain-of-thought text.
It is highly efficient at inference. Though, to be totally impartial, I should note that the training phase does take 2 to 4 times more compute.
Ah, there's the catch. Why is training so much heavier?
Well, they had to use a method called temporal parallel approximated training, using Jacobi-style fixed-point iterations.
Okay, stop. I'm going to need you to translate Jacobi-style fixed-point iterations into plain English.
Fair enough. So normally, recurrent models have to be trained sequentially, token by token, which breaks the parallel processing power of modern GPUs.
Right. One step relies on the previous step.
Exactly. So instead of doing it one by one, Jacobi iterations guess the hidden states for all tokens simultaneously.
Oh, they just guess.
Yeah, they make an initial guess, then use those guesses to calculate the next step, updating all the states at once in parallel. They repeat this iteratively until the values stop changing, reaching a fixed point.
So instead of drawing a picture pixel by pixel, you sketch the whole thing at once and continually sharpen the focus everywhere at the same time.
That's a perfect analogy. It keeps the parallel processing, but it does take more compute up front.
Yeah.
But here is the absolute biggest revelation of the entire paper.
The retrofitting.
Yes.
Yeah.
You don't have to pre-train from scratch.
This is wild to me.
The researchers took a pre-trained SmolM2 1.7b instruct model, an off-the-shelf open-source model. They surgically grafted this recurrent fusion pathway into its middle layers, did a brief fine-tune, and the gains held up.
Without a massive pre-training run?
Right. GSM-AK math scores jumped from 35.8 to 39.9, and MAP 500 jumped from 12.8 to 18.0.
Think about what this means for you or, any developer listening. You don't need a massive supercomputer to train a new model from scratch. You can take an off-the-shelf open source model, pop the hood, install this middle layer memory upgrade, and instantly get a smarter AI.
It dramatically lowers the barrier to practical adoption for continuous latent reasoning. You trade a bit of extra training compute for a highly efficient, demonstrably smarter inference model.
It's an exceptionally elegant solution. Let's just briefly recap this journey for you listening. We started by exploring how the bottleneck of standard AI tokens forces models to essentially forget their rich internal thoughts at every single step.
The unembed, decode embed bottleneck.
And then we saw how T2MLR's temporal middle layer recurrence fixes this by connecting the abstract reasoning centers over time,
Creating that internal neural bridge in the 20% sweet spot.
Exactly. And finally, how it can be retrofitted onto existing models for massive gains with tiny overhead using those Jacobi iterations to make training possible.
It really shifts our foundational understanding of how to build smarter AI.
It really does. But before we wrap up today, I want to leave you with a final lingering thought, something inspired by this research, but looking a bit beyond it.
Oh, this is the interpretability question.
Yeah, exactly. If AI models can now maintain a continuous evolving train of thought entirely within their hidden middle layers,
Without ever having to output those intermediate steps as tech.
right, How will we as humans be able to monitor or interpret what the AI is actually thinking in that quiet space between the words it actually says?
It's a profound alignment challenge. If the real cognitive processing happens in the dark, monitoring true intent becomes exponentially harder.
It's a fascinating and, frankly, slightly daunting frontier. Thank you so much for joining us on this deep dive today. Keep questioning the architecture, and we will catch you next time.